So I want to evaluate the integral from minus infinity to positive infinity of cosine of x over x squared plus 2x plus 2, the whole squared, okay? So the first thing I will do is I will write it as the real part of the same integral but with e to the ix instead of cosine of x, okay? Now I will find my poles as usual. So I will set the denominator equal to 0 and solve for x. And I get minus 1 plus or minus I. Okay. And you can also see that you have a pole of order 2. That means that the denominator is squared. Okay. So now I have an e to the ix here, and so I have an exponential, and so I need to know which path is more appropriate, like if it is this path or this path. Okay, in the upper half circle or along the upper half circle or along the lower half circle. Okay. So I will set my x equal to r times e to the I theta, and I will plug in that x, which is now equal to this r e to the I theta, inside my e to the ix, okay? So I will get e to the I r e to the I theta, okay? Now I will use Euler's formula. I will write this e to the I theta as cosine theta plus I sine theta, again inside this exponential here. And now I will take this I here inside, and so I will get e to the r times I cosine theta minus sine theta. Okay, this minus is because we have an I here and the I here, so we have I squared, so minus 1, okay? So now, if I want to get an exponential decay, so something of the form e to the minus infinity, I know that my radius later will tend toward infinity. I also know that this e to the I cosine theta is bounded, okay, because it's something of the form e to the I something that is bounded by definition. But what is important here is the sine of theta, okay? We have a negative sign here, and we have a r here that will tend toward infinity. Okay, positive infinity because this is a radius, it is a geometric distance. A geometric distance cannot be negative. I know that this e to the I cosine theta is bounded. I have a minus here and the sine of theta here. So my sine of theta needs to be positive in order to get my e to the minus infinity, okay? I want to get e to the minus r, where r will tend toward infinity. And so for that, if sine of theta would be negative, I would have negative, so positive, and I would get e to the infinity, which would diverge, and that's not what I want, okay? So sine of theta needs to be positive, and we know that for sine to be positive, we need to use our counter in the upper half plane, okay? Because sine is generally on the imaginary axis, and if the imaginary axis is positive, so above the real axis, sine is generally positive. If it's below the real axis, sine is generally negative, okay? In complex, if you are dealing with complex numbers, generally, okay? So we will choose this path in the upper half plane. So we will start at minus infinity as usual, so minus r. We will go like counterclockwise until positive infinity, so positive r, okay? And then I will go back to minus infinity through this circular path, okay? Yes, so, sorry. So now I only have one pole inside my domain, that is minus 1 plus I, okay, because minus 1 minus I would be outside of it. So if I calculate my residue, so as said, I have a pole of order n is equal to 2, so I need to use this formula for poles higher than degree 1. So I just plug in 2 instead of n, so I have 1 over 2 minus 1 factorial times the limit as x approaches my pole, so minus 1 plus I, because minus 1 minus I is not inside, times the first derivative, okay, because it is the 2 minus 1 derivative, so 2 minus 1, so 1, times my pole, x minus my pole squared, times my function, okay. And here I have factorized the denominator because I have two poles in total, even though only one is inside my domain. So I have factorized it. Okay. So now I can cross out this x minus 1 plus I and this one here, and so I'm only left with this part here and this part here. So this x minus 1 minus I squared, and so I can take the derivative of it, and then plug in my my limit as x approaches minus 1 plus I, and then I can divide through 1 over 1 factorial, so 1, so we don't really care about it, but still. Anyway, and at the end I should get, so I do all these manipulations here, and I should get e to the minus 1 minus I over 2I. Okay, that is my residue. Okay, it's not that clear, but it's that. Okay, it's e to the minus 1 minus I over 2I. Okay. Yes, so now I have my residue, my only residue, and now I can use the residue theorem as usual. So my contour integral, which is split into two parts. Okay, the part along the real axis and the part along this circular path is equal to 2 pi I times the sum of the residues. Okay. So now, as usual, I will try to prove that this second part vanishes as r gets toward infinity, so as the radius gets larger and larger, and that I will be only left with the part along the real axis, which is my original integral. Okay. Yes. So as usual, for this circular path, I will set x to be equal to r times e to the pi I t. Dx is equal to pi I r e to the pi I t, and t is between 0 and 1. Okay, as usual, this will give us this upper half circle. Okay, now we'll plug in everything in terms of t instead of x. So I have the integral from 0 to 1 because t is between 0 and 1. I have this e to the I r e pi I t because that is my x. I can plug in everything, but what's important is this exponent here, this e to the I r e pi I t, because now I can rewrite, as before, this e to the pi I t, I can rewrite it as cosine of pi t plus I sine pi t. Now I can take this imaginary number inside this I, and I get e to the r times I cosine pi t minus sine of pi t. Okay, minus because this is I squared, okay, so minus 1. And so as said, now I know that I have chosen the right contour because sine of pi t is positive in the upper half plane, and also it is also sine of pi t is positive for all t's between 0 and 1. Okay, if you plug in t is equal to a half, you get 1. If you get you always get something positive. So that's right. So we get positive here, negative here, positive infinity here, so we get something like e to the minus infinity, which will tend towards 0 as the radius gets toward infinity. Okay, and also as before, this e to the I cosine pi t, we don't really care about it because it is bounded. Okay, it's something of the form e to the I something, and you know that by definition is bounded. Okay, so now I have proven that my second part vanishes as our radius tends toward infinity. So the radius of this half circle. Okay. Could maybe write it a bit clearer. So if this is my half circle, that is my middle, that is my radius. It will tend toward infinity. Okay, and that was my second path, and that is my path number 1. And I go counterclockwise. Okay, from negative infinity to positive infinity, and like back like that. Okay. So now my second part is 0. My original part is, I said, the original integral. Okay, represented with this capital I. Okay, because if you are on the real axis, our integral goes from negative infinity to positive infinity, which is the case for our original integral, and it's the same function. Okay, so we could just plug in a dummy variable like set x equal to t and dx equal to dt, and then plug in everything, but then you would notice that this is in fact the same integral as here, just we have t instead of x. So it's the same thing. So we know that the original integral plus 0, okay, is equal to 2 pi I times the sum of the residue. Again, here it's positive. These 2 pi I are not negative. We don't have negative because we are doing our counter integral in a counterclockwise direction, okay? And remember, in math, counterclockwise is positive and clockwise is negative, okay? If you had chosen the bottom half plane, which would not work because we could not make this proof that the second part vanishes, okay? We could not prove it, but still, if you had chosen that and somehow we managed to get it correct, which is highly unlikely, but let's just suppose it, you would do our counter in the clockwise direction, okay? We'd start again at minus infinity, go to positive infinity, and then go back like that. So in a clockwise direction, and that would be negative, okay? But here we are in the counterclockwise direction, so we only have 2 pi I, okay, and not negative 2 pi I. Times the sum of the residue, so as said, you only have one residue, that is this e to the minus 1 minus I over 2I. So we can multiply that out. The 2 and the I cross cancel out, and you're left with pi e to the minus 1 minus I, okay? And now we can rewrite this pi times e to the minus 1 minus I as pi times e to the minus 1 times e to the minus I, because now we can use Euler's formula for this e to the minus I, and so we get p times e to the minus 1 times cosine of minus 1 plus I sine of minus 1, okay? So that is the value of this integral here. So the integral from negative to positive infinity of e to the ix over x squared plus 2x plus 2 squared dx, okay? Now our original integral had a cosine of x. So what we will do, as shown already here, is we will just take the real part of the final result, okay? Because remember that cosine of x is the real part of e to the ix, and sine of x would be the imaginary part of e to the ix. But here we have cosine, so we take the real part of this e to the ix, and we get we just take the real part. So we ignore this I sine of minus 1 because there is an imaginary number here, and so we're only left with pi e to the minus 1 times cosine of minus 1, okay? That is the real part. And we can see that cosine of minus 1, cosine is even, if I say no mistake, if I'm not doing a mistake. So cosine of minus 1 is equal to cosine of 1, and so we can write it as pi times e to the minus 1 times cosine of 1, okay? So that would be my final result, okay? So my final result is pi times cosine of 1 times e to the minus 1, okay? And so that is my final result, okay? So as usual, we have a cosine of x above the bar, the fraction bar. So we say that this is the real part of e to the ix. You do all the computation with e to the ix because this is a lot easier. Generally in complex analysis, if you do things with e to the ix instead of cosine of x or sine of x, you find the poles. You have a pole of order n is equal to 2. So you calculate your residues. You find which contour is more appropriate. If you have an exponential, okay, here we need to choose this path along the upper half plane, in the upper half plane. Yes, so we do a computation. We prove that this part along the circular axis vanishes. Okay. This is supposed to be a 2. That it vanishes, that we get our exponential decay, and not our e to the infinity, which would be really bad, and we would not be able to continue in this case. Yes, and then we use the residue theorem. Again, the part along the real axis is simply our original integral because we go from minus to positive infinity, and yeah, we have a simple real variable x. Okay, we can set x equal to t. It can be a dummy variable, but still, that is simply we're not dealing with something in the complex plane. Okay, we don't have something like I don't know, 3 plus 4i. Okay. That is not the case. So this is our original integral. Now we use the residue theorem. So we said that original integral plus 0, which is our counter integral, equal to 2 pi I times the sum of the residues. We have only one residue here. So we solve it and we get that. Now we use Euler's formula to rewrite this e to the minus I as cosine of minus 1 plus I sine of minus 1. And now we take the real part of that, because that is our original integral with cosine of x, and then we are done. So at the end we get pi times e to the minus 1 times cosine of minus 1, and cosine of minus 1 is equal to cosine of 1, so you get pi times e to the minus 1 times cosine of 1. Okay, yeah, so I hope it was clear, and I hope I forgot nothing and that you could read it, most of it, and yeah, thank you for watching.